Hi friends, today in this video we will discuss the most important concept in all of quantum mechanics, Schrodinger's wave equation. We will try to develop the Schrodinger's wave equation for a matter particle. So what is a matter particle? An electron. So we will strive to develop a wave equation describing the wave nature of an electron. We have to understand that Schrodinger's wave equation is a first principle in itself, and it cannot be derived from any other first principle. Something like Newton's law, F equals ma. Can we derive F equals ma from any other first principle? No, we certainly can't do it, because F equals ma itself happens to be a first principle. Similarly, Schrodinger's wave equation is a first principle, and the derivation what is possible with Schrodinger's wave equation is a heuristic derivation. So what do you mean by heuristic derivation? It is an in your own way type of derivation. So that's what we are going to do. We are going to develop the Schrodinger's wave equation in our own way. And Schrodinger, he worked on this particular equation for almost a year. He was contemplating on this after being inspired by de Broglie's concept of matter waves. He wanted to develop a wave equation describing the matter waves, and of course succeeded in his attempts, and he developed this equation in the year 1926, and he was promptly and correctly awarded the Nobel Prize for his tremendous insights into the development of quantum mechanics. So first let us ask certain questions, like why do we need a wave equation? We need a wave equation in the first place to systematically determine the wave function, that is psi. So we have already seen what psi is in the previous video. The variation of a matter wave is being described by the wave function, which is psi. Now the wave function can be expressed, if suppose we solve a wave equation, we can get a wave function psi of r comma t in three-dimensional space and time. Now next let us look at the various conditions. Are there any conditions for this Schrodinger's equation? Yes, of course, there are a lot of conditions. The conditions are, the Schrodinger's equation, it must be a linear equation. So what is the meaning of linear equation? It should obey the superposition principle. Suppose the solution of a Schrodinger's equation gives us a wave function, let us say psi1 of x comma t. So this is the solution of the Schrodinger's equation. Suppose we get another wave function as its solution, that is psi2 of x comma t. Now these two solutions or these two wave functions, they can be summed up, and we can write the superposition of these two wave functions as alpha psi1 plus beta psi2, and this is another wave function. So Schrodinger's equation should conserve the superposition principle, and that is only possible if it happens to be linear, and it turns out to be linear. Schrodinger's equation, it must be a differential equation of the first order with respect to time. The third point is, Schrodinger's equation must be consistent with these Einstein's and Planck relationship, that is, it should satisfy the momentum P equals h cross k and E equals h cross omega. Now we have already seen and discussed what h cross is. H cross is, in other words, is called reduced Planck's constant, and h cross is equivalent to h over 2 pi, where h is the normal Planck's constant. K is the wave number, which is the inverse of the wavelength, so k equals 2 pi over lambda. So first let us discuss the development of time dependent Schrodinger's equation, and let us say that all our conditions are only in terms of one dimensions. So first what we need to do is, we have to write a description, or we have to describe a plane monochromatic wave which effectively describes the electron. So such plane wave can be used or can be described by using this relation psi of x comma t equals a e power I kx minus omega t. So this is going to be our starting point, and let us call this equation as equation number 1. Now this equation can be rewritten. How it can be rewritten? We already know the relationship, like we have P equals h cross k. So from this we can tell k equals P over h cross. We also know this relation E equals h cross omega. So omega, or the angular frequency, can be expressed as E over h cross. So these two terms can be substituted in the wave equation, and this can be rewritten as psi of x comma t equals a e power I by h cross px minus et. So hope this is clear to all of you. So let's call this as equation number 2. Now let's try to differentiate this equation with respect to time. So that will be dou psi by dou t. Now let's go to the RHS. So we will be getting I minus I e by h cross, and this entire relation will stay as such. A is a constant, so A is the amplitude, so we can just have it as A. This is going to be the same thing, px minus et. Now we know that this is nothing but psi. So this equation can be written as dou psi by dou t minus I e psi by h cross. Or in other words, we can express E psi equals I h cross dou psi by dou t. So how do we get this relationship? So we rearrange the terms and find the relationship for E psi. Now which is going to be negative of h by I, and that can be written as I h cross. So we just want to eliminate the negative symbol, so we rewrite this equation as I h cross dou psi by dou t. Now what we are going to do is, we are going to differentiate this equation with respect to position, that is dou psi by dou x. And dou psi by dou x is going to be a e power I by h cross px minus et multiplied by I p by h cross. So we are only differentiating the term that is associated with x. The term which is associated with time is kept as constant, because this is a partial differential equation. Once again, let us try to differentiate this with respect to position. So it becomes dou square psi by dou x square, and we will end up getting a e I by h cross px minus it, and this will become minus p square by h cross square, because I square, since I square is a complex number, so I square is always minus 1. Now once again, this term can be written as psi, so we can express this equation as dou square psi by dou x square is equal to minus p square by h cross square psi. So from this we can say that p square psi will be equal to minus h cross square dou square psi over dou x square. So we have got a term for p square psi like what we got for E psi. You may be wondering why we need all these things. So just please be patient for a second, everything will be revealed. Now let's suppose that we have a free particle The electron is not being acted upon by any other external force. In that case, the total energy of the system is going to be P square over 2m. And if this is operated with the wave function psi, we are going to get E psi equals P square by 2m psi. Now we know the values for E psi and P square psi. So if we substitute those values, we will be getting I h cross dou psi over dou t is equal to minus h cross square by 2m dou square psi by dou x square. So technically speaking, this is the Schrodinger's time dependent equation. However, we are assuming that this free particle is acted upon by a force. So when a free particle is being acted upon by a force, we should also include the potential energy component. So this total energy will become E psi is equal to P square by 2m psi plus V psi. So this Schrodinger's equation can be rewritten for a constant force field as IH cross dou psi by dou t is equal to minus h cross square over 2m dou square psi by dou x square plus V psi. So this is the famous Schrodinger's time dependent equation. This is such a powerful equation that any problem in quantum mechanics starts or can only be started by solving the Schrodinger's equation. Please understand that Schrodinger's equation is a complex equation because it has got this imaginary number which is I. So you cannot have a situation where you have completely real entities on one side, and if you have an imaginary component in the other side, you cannot call that as a real function. It is a complex function, it is a linear equation and first order with respect to time, and it completely satisfies the relationship P equals h cross k and E equals h cross omega. So we have got this Schrodinger's wave equation. Please understand that we have not derived it. We have done some mathematical jugglery here and there, and we have obtained this equation. Now there is another variation of Schrodinger's equation which is called the time independent equation. Time independent equation. So how it is done? It can be done with just one step. So let's consider this equation once again. The total energy of the system being E psi equals P square psi by 2m plus V psi. Here the energy evolution doesn't depend upon time. So we need not substitute the value of E psi, rather we substitute the value for P square psi, and that's going to be minus h cross square by 2m dou square psi by dou x square plus V psi. So this equation can be rewritten as dou square psi by dou x square, let me get this symbol properly, plus 2m over h cross square E minus V psi equals 0. This is the famous Schrodinger's time independent equation. On many occasions and contexts, we would like to use this equation where the time will be totally irrelevant. In all those instances, for instance, in the next video we are going to discuss about a particle in a box, where you don't need the time dependent equation, we just need to solve the time independent equation. And that's what we are going to look at in the next video. In the next video, we will try to solve and develop the eigen energy value and eigen energy wave function for a particle trapped inside a box. So, thank you very much.